Every single digital device, I don't care if it's your watch or a massive supercomputer, it all boils down to three really simple ideas. It needs a heartbeat to keep time, a way to do some basic math, and a way to remember what it just did. So today, we're going to break down these three core building blocks of all computation. And that really is the big question, isn't it? How can a bunch of simple on-off switches do everything from sending a text message to helping us explore the stars? Well, the answer, the secret sauce, is all in how these simple switches are cleverly combined to do specific jobs. We're going to look at the three key combinations that honestly make everything else possible. So, first things first, let's talk about timing. Every single computer needs a pulse, a steady rhythm, to make sure all of its parts are working in perfect sync. You can think of this as the computer's heartbeat, and we call it the clock signal. A clock signal is, believe it or not, incredibly simple. It's really just a voltage that switches between high and low, a 1 and a 0, over and over again at a super fast and consistent rate. This constant rhythmic pulse is basically the metronome for the entire computer, making sure every single component does its job at the exact right moment. Now, inside that simple wave, there are these really important moments. The first one is called the rising edge. This is the exact instant the signal flips from low to high, from a 0 to a 1. Think of it like a starting pistol that goes off and tells the component, okay, do your thing now. And of course, what goes up has to come down. The falling edge is that moment the signal drops from a 1 back down to a 0. So together, one rising edge and one falling edge make up a single clock cycle, one complete heartbeat of the machine. So why is this so important? Well, a computer is doing millions, if not billions, of things at once. Without a clock, it would just be pure chaos. This slide really shows how the clock brings order to that chaos. On the first clock cycle, maybe the CPU fetches an instruction. Then, on the second tick, it sends some data. On the third, a device writes something to memory. Every single step happens in its own little time slot, which prevents everything from crashing into each other. The clock is the ultimate traffic controller. Okay, so we've got a rhythm. Now let's add the brains. How does a computer actually calculate anything? Well, that brings us to our second building block, logic gates that can perform basic math. At the very heart of all computer math is a circuit called an adder. The simplest version is the half adder, and it just adds 2 single bits. But to add numbers bigger than 1, you have to handle a carry, just like in grade school math. And that's where the full adder comes in. It can add 2 bits plus a carry from a previous addition. Let's take a look at how the simple half adder works first. So half adder takes in 2 bits and gives you 2 outputs, a sum and a carry. Let's just focus on the sum for a second. If you look at this table, the sum is a 1 only when the 2 inputs are different from each other. This is the job of what's called an XOR gate. But wait, look at that last row. When we add 1 and 1, the sum is 0? So where did the value go? And that brings us to the second output, the carry. Now look at this table. The carry is a 1 only when both of the inputs are 1. This is done by an AND gate. So with just 2 simple logic gates, we can add. But the half adder has that limitation. It can't accept a carry from a previous calculation. So to add bigger numbers, like 11 plus 11, we chain these full adders together, passing the carry from one to the next, just like you would on paper. All right, we have heartbeats and we have a basic brain. But what's the point of calculating something if you immediately forget the answer? So the third and final piece of our puzzle is memory. How does a machine actually hold on to information? The most basic component of memory is called a flip-flop. Yeah, it's a bit of a quirky name, but the idea is actually pretty simple. It's a circuit that works just like a light switch. You can set it to on to store a 1 or flip it to off to store a 0, and it will just hold that value until you tell it to change. One of the earliest versions of this is the RS flip-flop, which stands for set and reset. If you set it, the output becomes a 1. If you reset it, the output becomes a 0. And if you don't do anything, it just remembers whatever it was before. But here's the big problem. What happens if you try to set it and reset it at the exact same time? The circuit just gets confused. It enters this invalid state, and we absolutely can't have that in a computer. So this leads us to a really crucial question. How do we build a memory switch that avoids this whole invalid state problem and only changes exactly when we want it to? And the answer is the D-type flip-flop. And this is where that first concept we talked about, the clock, comes back into play. This smarter switch has one data input, D, and a clock input. It elegantly solves the problem by only paying attention to the data on the rising edge of that clock pulse. By synchronizing the memory to the clock, it completely avoids that invalid state. It's a perfect, predictable memory cell. Okay, so we've got a way to reliably store one single bit of information. But computers don't really work with single bits, right? They work with bytes and much, much larger chunks of data. So how do we scale this whole thing up? So here it is, a reliable little building block, one D-type flip-flop, and it can store one single bit, a 0 or a 1. To store more useful information, like a number or a letter, all we have to do is group them together. And it really is this simple. To store 8 bits, which is 1 byte, you just take 8 of these D-type flip-flops and you line them up right next to each other. Then you connect all of them to the very same clock signal. Now, on every single clock pulse, all 8 of those flip-flops capture their data at the exact same instant. And together they form what we call an 8-bit register. So we've seen the clock for the rhythm, the adder for the brains, and the flip-flop for memory. Now let's see how they can combine to actually do something useful. A perfect example is a digital counter. It uses a series of flip-flops to store the current count. That's our memory. Then, on each pulse of the clock, that's our rhythm, an adder circuit increases that number by 1. That's the computation. The new value then gets stored right back in the flip-flops. It's the simple, elegant loop of all 3 of our building blocks working together in harmony. You know, a great way to think about this is like a turnstile at a stadium. The clock pulse is like a person walking through, and each one of those pulses causes the counter to click and add 1 to the total. It's really that simple. So that's really the core idea. From a simple ticking clock, some gates that do basic math, and switches that can remember, we can build circuits that count. Now think about this. A simple digital counter uses a handful of these components. Your phone uses billions of these same fundamental blocks, all working together in perfect synchrony to create the complex digital world we use every single day. From the simplest rules, incredible complexity emerges.